Hi, my name is Luke Aber, and I will be presenting a research paper in ICS Cybersecurity for my Georgia Tech Introduction to Cyber Physical System Security course, ECE 8813. The paper that I'll be presenting is on ZOE, content-based anomaly detection for industrial control systems. So for the paper details, these are the three authors: Resniger, Kellner, and Rieck, all from the Institute of System Security, TU Braunschweig, which is in Germany. The paper was presented at IEEE IFIP Dependable Systems and Networks Conference in 2018. So as of this recording, this paper is only a few years old. And for those who are unfamiliar, the IEEE is the Institute of Electrical and Electronics Engineers, and the IFIP is the International Federation for Information Processing. The topic of this paper is intrusion detection on ICS networks by methods that have been largely discarded by the network intrusion detection community as far as its application to proprietary binary protocols typically found in ICS networks. Some form of network intrusion detection is an essential element of a robust IT cybersecurity monitoring program, and the science of intrusion detection in business and home networks has matured a great deal in the past few decades. But intrusion detection in ICS networks lags behind its business IT counterpart due to those networks' use of specialized protocols and the prohibitive barriers like cost and accessibility for cybersecurity researchers to working with those protocols. So just to drive home why this is a significant problem and why it's worthwhile to do research on this problem. Content-based IDS has till now been perceived as being ineffective in detecting attacks in industrial protocols because these protocol specs are rarely published by their vendors. It's difficult to detect anomalies in a protocol's traffic if you don't have a definite grasp of what its normal messages look like. This, of course, is less of an issue in common IT protocols because many of the protocols are made available through RFPs or standards documents published by standards organizations. Since IDS protocol details are largely kept a secret, the next best option for determining what is normal is to make inferences from observed network traffic. And that is the approach that the research team in this paper takes. Don't forget, though, that simply knowing what is normal isn't all that matters. Knowing which deviations from normal are so abnormal as to be suspicious or malicious is another important part of intrusion detection. Again, something peculiar to ICS networks is that network captures of malicious events are hard to come by. They're fairly scarce. This makes it even more difficult to develop intrusion detection systems that can spot malicious activity. So in this research, the novel approach to intrusion detection for content-based intrusion detection is prototype models. Prototype models are a special type of content models, and any type of content model is essentially its job is to describe something. So in this case, we're trying to describe a certain network protocol that's used in an ICS network. For the first step of creating a prototype model, the first step is to generate n-grams of a specific length from each message to generate a vector of n-grams that represents the message. So we're basically trying to generate this vector of n-grams. N-grams is just the substrings found within a message that are sequential characters. So if we're taking, say, n equals 5, it'll be a 5-gram, and then 1, 2, 3, 4, 5. 2, 3, 4, 5 creates this first n-gram. And then likewise the second n-gram, and then the third. So this is what we're trying to create, a vector of features, which is a set of unique n-grams that will characterize the message. I'd also like to point out here that the vectors of n-grams, they are all unique, but if any n-grams did repeat within a message, say if 01001 occurred multiple times within a message, ZOE and the prototype model creation of n-grams it's going to keep a count of how many times that specific n-gram occurred within the message. And this count that shows the frequency of n-gram occurrence is crucial for the noise reduction methods explained in the coming slide. So part 2 of creating our prototype model is to create a breakdown of n-grams as a set of features common to messages in a protocol to determine which parts of a message are going to be constant and which are going to be variable and which are going to be volatile. Looking at the far left, we can see an example of something that's variable within a protocol. So this is a certain location within messages in a protocol that we can expect to change. So we see the first 2 bits here. This is a series of 5 messages, 5 individual messages. In each of these 5 messages, the first 5 bits, or the first 2 bits stay constant, and the 5th bit stays constant. But you see here in the 3rd and 4th bit, this is apt to change. So we would think of this as being variable. In the red frame, we see something that stays constant among all 5 messages. So this is a feature of the protocol. We could assume if this is our entire sample set, this is a very small sample set of 5, we could assume that this is a constant feature of this certain protocol that will have this set 11101 at this spot in each message. And then lastly, we want to note if something is volatile, meaning that we shouldn't expect to find a pattern at this certain location in messages for this protocol. So you see that we can't find any discernible pattern here, and we would call this volatile. Just to drive home the point, this is a rule created based on a series of sample messages to determine which parts of a message are variable or volatile. So you can see here that for each message up until HAJ, the ASCII data stays the same. But once we reach past J, we have an area that is apt to change. So we would call that variable. And then same past X, this is variable data. And then this is also apt to change. So we make a rule here saying that for this protocol, we expect this data to stay the same up until this point. And then we might expect some differences here between messages, some differences here between messages, and some differences here between messages. So lastly, also critical to the success of our intrusion detection method here presented in this paper is its success in noise reduction. So after separating the messages into vectors of n-grams, a frequency threshold, T, should be selected so that any feature or n-gram that doesn't occur at least T times in a sample set of messages or a set of sample messages, see we have 3 here, any n-gram that doesn't occur at least T times shouldn't be included. It should be discarded as not important or not characteristic of the protocol's prototype model. So this is a way of filtering noise out. This method of noise reduction works well for industrial binary protocols because of their concise nature, which is driven by the need for low latency network transfer by minimization of communication overhead. So just to step through the noise reduction, we're taking a threshold of T, so we're going to mark to keep anything that occurs at least 3 times among messages. So you see 10011 is kept 3 times, and then feel free to pause the video to check me, but these occur 3 times, and I'm marking out those that don't occur 3 times because they didn't meet a frequency threshold. So those would be discarded as valid features to put into our prototype model. And this achieves noise reduction in trying to determine which are defining features of our protocol. So lastly, once the prototype models are created and the noise has been reduced by this method, ZOE, our intrusion detection system or method, has now been trained to expect messages of a certain protocol to have certain features as defined by their prototype models. And now, once we have our models created, if we apply ZOE to a live network and try to detect intrusions, if any new messages do not conform to the protocol's prototype model, ZOE reports an anomaly. So as for the experiment described in this paper, to test ZOE, researchers collected about 200 gigabytes of network data over 6 days at a coal mining facility and an adjacent coal burning power plant. Data collected at the control level was collected during generator startup event and during steady operation and the control network servicing a 500 megawatt generation unit in the plant. The network data captured included several industrial protocols, but the researchers chose only the 5 most prominent ones for the sake of having a good sample size for the clustering for the prototype model creation. The traffic captured related to the generation unit was network traffic at the control level. So you can think here, operator control or supervisory control traffic. And this is to be contrasted with the field level traffic that they collected as well. So for good measure, they also captured traffic at the field level and the generation facility. The devices at this level were communicating via Profinet IO, which is not an IP-based protocol in operation. Altogether, the researchers collected data from 92,700 field and control devices, which is a staggering number that gives some indication of the size and complexity of this ICS they used to conduct their research. As mentioned before, only the 5 most prominent protocols on the control network used in the experiment. 2 of them are UDP-based and 3 were TCP-based. The field level protocol was Profinet IO, a protocol commonly used in communication among PLCs and IO modules. Since the intrusion detection method in this research was purely content-based, the message or payload of each of network messages from these protocols had to be extracted from the network captures. For UDP, of course, this is the datagram itself. For TCP, it's the reassembly of the TCP session between devices, and for Profinet IO, it's the parsing of the raw Profinet IO packets traversing the network. After collecting their sample data, the researchers found that for these protocols, the incoming messages for a device differed vastly from the outgoing messages. And this was only for some of the protocols. But this does make sense when considering the typical relationship between devices, especially at the control level. There is commonly a monitoring and controlling device that's communicating, quote unquote, down to a monitored and controlled device. The message from the monitoring device can take the form of something so simple as, give me all your points in such and such point map. And the monitored device could respond to such a request with possibly hundreds of point value pairs. These messages are of the same protocol, but they would take very different forms and so warrant the creation of an incoming prototype model and a separate outgoing prototype model, even within the same protocol. As mentioned at the beginning of the presentation, examples of real-world attacks on ICS networks are pretty scarce. So the researchers resorted to generating their own attack messages to inject into test data. They created the attacks by substituting malicious data into normally benign messages of a certain protocol. Here's an example of an attack created from a rule that was shown in a previous slide that identifies the locations of variable data in a message. You'll remember this from a previous slide. We had constant data and then areas where data could vary within a message. So this is our rule, and we'll use that rule to substitute some malicious data into a spot that could have variable data. Notice too that even though these didn't have to be the same or legitimate data, for this attack, they did keep a legitimate combination of other variable data the same, so as maybe to make it a little bit harder for ZOE to detect an anomaly. So to measure the detection results of an IDS, the ideal of any intrusion detection system is to detect all the attacks on the network and to not send up false alarms for benign or legitimate traffic. The receiver operator characteristics, or ROC curve here, lends itself well to illustrating the efficacy of an IDS. The y-axis here on this chart is the true positive rate, and the x-axis is the false positive rate. The shaded area is called the AUC, or the area under the curve. A perfect IDS would have a 100% true positive rate and a 0% false positive rate. And so the ROC curve would be a vertical line coinciding with the y-axis, and of course the area under the curve would be 0 because it's a vertical line. However, there's no IDS that I know of that has such a ROC curve or an area under the curve, so it's common practice to put an upper bound on the false positive rate here on the x-axis. And you can see this upper bound here as being this gray vertical line leading up to the ROC curve. So this represents a upper bound on the false positive rate at 50%, which is a rather high or permissive tolerance for false positives for a real IDS. But essentially, no matter where the upper bound on false positive is, the question that you're asking is, how high can my IDS get the true positive rates to be while staying under such and such false positive rate? So keeping in mind the area under the curve explanation and the false positive rate bound explanation from the previous slide, see this graph of the results from ZOE's intrusion detection. The results are separated by protocol here on the bottom, separated by protocol, and furthermore for P1, 2, and 3 by inbound and outbound traffic. The darker bar is the true positive, represents the true positive rate while keeping the false positive rate under 1%. And the lighter bar represents the true positive rate while keeping the false positive rate bounded under 0.1%. So that would be a much more stringent operating condition or stringent requirement for your IDS to operate under. Notice that the drop in the true positive rate for the more stringent false positive bound is not very significant for most protocols. So you see here, whenever we made our requirements for the IDS more stringent, going from a 1% false positive bound to a 0.1% false positive bound, there was only a slight reduction in the true positive detection for protocol 1 in, and same for protocol 1 out. However, there could be some exceptions here for protocol 2 in, for protocol 3 in. You see here that whenever we put that bound for false positive rate, we shifted it from 1% to 0.1%. We did get a non-negligible reduction in true positive detection, maybe down to 97 here and 96 here, or yeah, somewhere around there. Anyway, it's non-negligible. However, if you look out to the far right of the graph for P4, P5, and P6, even when reducing or tightening that bound for false positives from 1% to 0.1% for P4, P5, and P6, ZOE still performed at 100% true positive detection for these 3 protocols. So that's pretty encouraging, and across the board, the researchers were rightfully satisfied with these detection results from ZOE. The ZOE IDS takes in 2 parameters for tuning. You can see them here. The first number is the number of message groups to consider in training data for the development of the prototype models. And the second is the frequency threshold. which was mentioned in previous slides for the purposes of noise reduction. So here are the results of ZOE when researchers varied the frequency threshold and kept the message group count at 1, which is also known as using a global content model. While changing the threshold doesn't make much of a difference for false positive bounds above 0.1%. Looking to the graph, these 3 lines represent ZOE's performance with different false positive bounds applied. So this is at a false positive bound at 1%, this is at a false positive bound of 0.1%, and this is at a false positive bound of 0.01%. So very stringent requirements here. Notice here that once we get past about 30 for the frequency threshold, for both of these curves at 1% and 0.1% false positive thresholds, after you get about 30, no matter how much you increase the frequency threshold, you don't get much of a reaction or much of a difference in true positive detection, even with the 0.1% true positive tapering off here. But the responsiveness of the curve for the 0.01 false positive bound, it's much more responsive. And so this is something interesting to look at and can shed more light on optimizing your frequency threshold. So you see here that there is a definite optimal point here at about 35 for frequency threshold whenever you hold your false positive bound at 0.01%. So that's valuable in tuning your intrusion detection system. Something else to note though here is that even whenever you hold your false positives to 0.01%, which is very stringent compared to the others, you still get a true positive detection rate at 80%. So you're detecting 80% of your actual malicious events going on in your network. This could be acceptable or maybe even desirable, especially if you consider whether this intrusion detection system might eventually turn into an intrusion prevention system, where false positives you will want to reduce as much as you possibly could because they could possibly disrupt ICS operations. To contrast this work with related work, this work of course used purely content-based anomaly detection, which has been largely discarded by the ICS security community because of the issue of having little to no information about proprietary protocols in use. But other methods include meta-network anomaly detection and physics-based anomaly detection. Meta-network anomaly detection is basically the opposite of content-based, in that meta-network anomaly detection tries to detect anomalies based on everything except content. So frequency, telemetry data, anything except the actual message payload. And physics-based anomaly detection attempts to model the physical state of ICS processes or a system and alarm on significant or odd deviations from that expected state. The research conducted and presented in this paper is a valuable contribution to the ICS network security field, especially in that it challenges, and in my mind, overturns some of the widely held assumptions about what can be done in the way of content-based anomaly detection in industrial protocols and industrial networks. So in conclusion, a high true positive rate and low false positives, that's a good IDS. And ZOE, at least in this experiment, it performed in such a manner. I'd be interested to see how it performed in the future on live networks and just trying to expand the protocols that it was tested on. And on that note, the experiments on the six distinct protocols lends credibility to the effectiveness of ZOE. You know, the takeaway for this is that content-based anomaly detection isn't dead. for ICS networks. It's not a lost cause, even though it is difficult to determine the structure and contents of binary protocols on ICS, and even though we don't have insight or inside knowledge on the construction of those protocols and the structure of them, machine learning can go a long way in helping us to understand what ICS messages should look like on a network, and better get how to spot anomalies in them and possibly detect malicious activity. And this concludes my presentation. So thank you for listening.